Hello everyone. In this video we'll be discussing arithmetic and geometric sequences, which are very particular types of sequences. Arithmetic basically has to do with adding the same thing each time to get from one term to the next, and geometric has to do with multiplying instead of adding, basically. We'll be discussing the sequences as well as the sequence of partial sums for each of those types of sequences. So first here, let's take a look at arithmetic. And I say here an arithmetic sequence has what is called a common difference, which we call D. Now, common difference is basically you add from each term, from one term to get to the next term, basically. So we add D to get from A0 to A1, to get from A1 to A2, from A2 to A3, and so on. So we can say that a recursive way of defining this type of sequence is that A sub n is A sub n minus 1, the previous term, plus the constant D. Okay? Now, something you may notice here is that I'm starting with 0 instead of the usual 1. As it turns out for arithmetic and geometric sequences, though you could start with 1, the closed forms for their general terms end up looking a lot nicer when you start at 0 instead of 1. So the closed form here is A sub n is A0 times n times d. And that's actually not very difficult to describe. For example, if you wanted to jump from A0 to A3, you would add 3 of the common differences to that to get from here to here, just to kind of jump through. Now, instead of jumping through one of them at a time and generating the sequence, you can just get to this one to the third one by adding 3 d's to it. So A3 would be A0 plus 3d, so you kind of see that right away. So I think that's a little more obvious then. Okay, so now we're asked to find the 30th term for each of these sequences, which is a lot. Now, when I say 30th term, you have to have an understanding of what we mean by term. Like, is this the first term or is it the 0th term, right? Depends on how we define things. So I'm defining this starting at 0. I kind of set the tone at the very beginning here. If you were given a problem and it says that and it doesn't say start at 0, you may think that they're probably saying start at 1. It depends. I mean, it's really not super obvious. So they should say it in a question if it's not stated. Maybe just to kind of emphasize, I'm going to write here, n goes from 0 to infinity, which I'll write as maybe n is in the set natural numbers with 0, just so we know that this is the 0th term. So the 30th term, will that be a sub 30 or is it going to be a sub 29? Again, we can find both. The way I'm going to do it is the same. So the first thing I want to do is I want to find the common difference. So here we have the common difference is just 3 then. Now why it's called a difference, even though we're adding from one term to the next term, is because if you take the successive difference of these terms, you get the common difference. 13 minus 10 is exactly what you need to get from 10 to 13. So the common difference here is then just 3, we know this. So assuming this is an arithmetic sequence that continues in that fashion, we found that d is equal to 3. Perfect. And furthermore, based on what we've set up here, we know the general term is then going to be A0, which is 1, plus 3 times n. And we can verify that when you plug in 0, you get 1. When you plug in 1, you get 4. When you plug in, 5, or maybe 4 would be better, right? If you plug in 4, you go 1 plus 3 times 4 is 1 plus 12, which is 13. And that indeed gives you this a sub 4 term, okay? So with that being said, we can actually find a sub 30 by plugging 30 into this. So when you plug 30 into this, you get 90 plus 1, that's 91. So that would be what I consider to be the 30th term of the sequence, where this is the 0th term, so that's pretty important. Otherwise, the 30th term, if this was the first term, would be a sub 29, which would actually just be this minus 3, so that'd be, 88 in that case. So again, something to think about. It depends on the context, depends on the wording. But here, if I put this, then I'm saying the 30th term is the a sub 30 term. Which now, kind of thinking about it, maybe I want to kind of take that back and say it's really a sub 29. But again, it just depends on how you word things. So for me, I'll say the 30th term. Instead of saying that, I'll say the a sub 30 term just to be a little more clear. Okay. But that kind of throws me off here because I'm using b sub n instead of a sub n. So let's just call this the n equals 30th term. That sounds better. Where we start is 0. So I'll emphasize that with each of these. And again, for arithmetic and geometric sequences, it's better to start with 0 because the closed form for the general term comes out a little nicer. So here, what is the common difference? What do you add to get from one term to the next? Well, you're actually subtracting, notice. 17 minus 6 is 11. And does that work all the way through? Let's see, 11 minus 6 is 5. 5 minus 6 is negative 1. That works. So negative 6 is the common difference here. So very quickly we can see that the closed form is going to be a0 plus 6 times n, or negative 6 times n. So then b sub 30, the n equals 30th term of the sequence, plugging 30 into this, we get, well, let's see, 3 times 6 is 18, so times 30, it's 180. So we have 17 minus 180 is like negative the quantity 180 minus 17, which I guess is 163. So I'm getting negative 163 for that. Perfect. Awesome. Okay, great. So with that being said, let's now talk about geometric sequences, and then from there we'll talk about the partial sums of each of these. So here, very similar to what we saw for arithmetic, geometric sequences have common ratios, which we call R. Where a common ratio is what you multiply from one term to get the next term, from one term to the next. So here we say that R times A0 is A1, R times A1 gives you A2, and R times A2 will then give you A3. So recursively, we say that A sub n is R times the previous A sub n minus 1 term. And the closed form would then be A0, an is equal to A0 times R to the n, which again makes a lot of sense because if you consider, for example, A sub 3 as an example, notice to get from A0 to A3, you multiply 3 R's, R times R times R 3 times is R to the third. So if you replace those 3 with a general n, then you get that. So that's what happens in general. So it's pretty easy to see that, again, if you start from 0. If you start from 1, it's harder to see the connection. It's harder to talk about these things. Okay. Now, here for this example, I'm asking you to find the common ratio and closed form for these following sequences. So first, let's find the common ratio. What do you multiply to get from one term to the next? And the reason why it's called a ratio is because we're dividing the one term by its previous term. Kind of like with common difference, you can find it by taking the difference between a term and its previous term. So notice here, 40 minus 80, not 40 minus 80, but 40 divided by 80, my mistake, the ratio, is 1/2, or reduces to 1/2. And multiplying 80 by 1/2 indeed gives you 40. That times 1/2 is also 20, that times 1/2 is 10, and 10 times 1/2 is indeed 5. Now I like to think of it like multiplying instead of dividing. It just kind of seems a little easier and more intuitive. Great, so now with that being said, the closed form, so well, maybe I'll write it down because it's part of our answer. You're finding the common ratio, R is equal to 1/2, perfect. And now we can say the closed form is then the first term A0 times the ratio 1/2 to the nth power, perfect. There's your closed form for a general term along with our common ratio below. Fantastic. The next one's also pretty simple. Notice that times 3 is going to give you this. This times 3 is indeed that. And you can check 54 times 3 is indeed 162 as well. So assuming that continues, the common ratio of this geometric sequence is 3. The closed form is then the 0th term, the first term 6, times 3 to the n. And again, for these sequences, we assume to start at 0. So when n is equal to 0, 3 to the 0 is 1, 6 times 1 is 6. Here, 1/2 to the 0 is 1, 80 times that is 80 for the first term. Fantastic. So now with that being said, now let's take a look at the partial sums for arithmetic and geometric sequences now. Okay, so here let's first recall the triangular numbers, 1 plus 2 plus 3 all the way up to n. It's probably the most, simplest case, simplest example I should say, of an arithmetic partial sum. So here the arithmetic sequence is just n, right? It's just 1, then 2, then 3, and then 4, and so on. So adding up all of those, you get this. So this, of course, is the sum from, let's say, I guess we can use k as our index, that's fine. From k goes from, I guess we can say 1 to n of, kind of sounds weird, but we're ending at n, we're plugging that into k. Again, it sounds funny, but you plug it in by typing, or by plugging in k equals 1, and for k you get 1, and then when k is equal to 2, you get 2, and then all the way up to n. So this is that in sigma notation. Now, generally how this is kind of shown and proven is by writing this in two different ways. We can write it in the usual way, and then we can also write it in the reverse order. So n, then n minus 1, then n minus 2, and then all the way down to 3, then 2, and then 1. But what you notice is that when you add these together, kind of pairwise vertically, 1 plus n is n plus 1, 2 plus n minus 1, well 2 minus 1 is 1, so it's also an n plus 1. 3 added to this is also n plus 1, and then actually the last term here is going to be n plus 1. Okay, so this is actually 2 times the sum, t sub n, and notice here we know how many of these terms there are, because there were n many terms above, so this is in fact just n times n plus 1. That's after all what it means to multiply something by n, is to add it to itself n times. So then dividing by 2, we get the formula that we saw earlier. T sub n is n times n minus 1, or n times n plus 1, sorry, all divided by 2. So that's a way you can actually show what a general term of a sum is. And if you wanted to find this sum, for example, you do the same thing, just write it in the reverse order. The only issue is you need to know how many terms there are, and we don't know that. I haven't shown how to do that yet. There are a few ways. I think the best way to do it, though, is to notice first off this sequence, 2, 5, 8, 11, 14, is indeed an arithmetic sequence. And the common difference here is 3. You add 3 to get from one term to the next. Perfect. So we know d is equal to 3. Fantastic. And then that tells us that the closed form is then going to be 2 plus 3 times n. Perfect. Now, with that being said, so it gets kind of funny, but let's just kind of think about it for a second. With that being said, if this is the general term for the sequence, then when our last term here is 470, we can actually solve for n to see what term that is. So I hope this makes sense. All of these numbers are of this form, 2 plus 3n. So this is when n is equal to 0, when n is equal to 1, when n is equal to 2, when n is equal to 3. And you can check by plugging these in. For example, when n is equal to 4, 4 times 3 is 12, plus 2 is indeed 14. So what is this? What is n equal to when the result is 470? Well, just set it equal to the general term in the closed form. And you can find just by solving. So let's subtract 2. We have 468. Can we divide this by 3? Well, I know 45 divided by 3 is 15, and that's 18 less than 450. 18 divided by 3 is 6, so it's 156. So this is actually the 156th term. And you can check, 156 times 3 is indeed 468, checks out, plus 2 is 470. Fantastic. Okay, great. So we know how many terms there are. Well, kind of. Here we said there were n terms. So here are there 156 terms? Not quite. In fact, if you think about it, counting these first 4, these are 4 terms. Just kind of going back to that debate we had earlier, where I said find the 30th term. Do I mean a sub 30 or a sub 29? Because the first 4 terms is up to n equals 3 here. So we have to know how many there are, so we're going to have to subtract 1. Or I guess, let's see, subtract 1 or add 1. I guess you add 1 to the subscript, right? So if you go up to n equals 3, there's actually 4 terms because you're including 0. So that means here there's a total of 157 terms. Okay, so let's write that. 157 terms. So now what we're going to do is I'm going to have to erase some of this stuff here. I guess I can erase this, it's fine. And now what we're going to do is we're going to write this in its kind of reverse order, and we're going to call it, I'll just call it S for sum. So the sum is 2 plus 5 plus 8 plus all the way up to 470. Okay? And writing it in the reverse order, we have 470, and then 3 less than that is 467. 3 less than that is going to be 4, 64, all the way up to the first term here is 2. And clearly what you end up getting is 472 all the way through. But what's kind of interesting is that you don't need to like notice that. Maybe you need to notice it, but you don't need to like actually see it every time. Once you kind of see it the first few times, you realize that because of the way common differences work, if you add the first to the last, the second to last, the third to the last, you get the same number all the way through. So you're kind of folding this sum in half in some sense. So in reality, this term you're going to get that's added to itself that many times is just the sum of the first and last term. When I say first term, I mean the 0th term here. Okay, so that's 2s, and we know there are 157 of these things. So then finally just divide by 2. We get s is equal to this thing, 157 times 472, all divided by 2. It's a very large number. I guess I could do it right here live. Let's see. So, well, not live, we're being recorded obviously, but I didn't practice this or anything. So dividing 472 by 2, we get 236. So what's 157 times 236? I don't know, I had in mind to maybe do this by hand on the board. It just takes too long. But we get 37052. So that's 37,052. Perfect. Now, what's really nice is that from this, we get this kind of general form. So in general, we get the following. The sum from n equals 1 to infinity, n equals 1 to k, n equals 1 to k of an arithmetic sequence a sub n is going to be the, let's see. So we know 472 it came from the sum of the first and last term. Just like here, the first and last term add to n plus 1. So we're adding that to itself however many times we have, how many terms we have. So if you go from 0 to k, there's k, or from 1 to k, excuse me, there's k terms. Okay? And then the sum of the first and last term, a1 and ak, like that, and then all divided by 2. So that's a general way of writing this. Now, again, we start at 1 here, just because it's easier to talk about for that. So what about if we started at 0? Because I know, again, starting at 0 sometimes, starting at 1 sometimes, it gets kind of confusing. So let's see what happens if we were to start at 0 instead. So if we were to start at 0 instead, 0 to k, we're still adding the first and last term. So this is still a0 plus ak. That's fine. Now how many terms you have is the difference of these two plus 1. So from 1 through k, there's k terms, or 1 through n, there's n terms. From 0 to k, there's k plus 1 terms. Okay? And I hope that makes sense here because we said that this is the 56th index term, but there's a total of 1 more than that because you're starting with the 0th one. And that adds 1 more term, basically. So there we go. We have, and I don't know why I wrote it like that, sorry. That looks really goofy. But this is supposed to be equal to, maybe I can squeeze it in here, the sum from n equals 0 to k of a sub n. So I wrote it kind of weird earlier just now. So we have these two different ways of writing it. Like this if you start at 1, which is actually better for sums, or like this if you start at 0, which is actually kind of weirder looking for sums. But what's nice is that we actually have a method we can use, but the weird part about this method, and even if you didn't use a method and use the formula, you would still have to know how many terms there are, which may not be obvious in the problem. Okay, so with that being said, I'm going to actually move on to talk about now geometric sums. Alright, so here I want to first recall a sum we kind of saw before. And this looks like it's infinite, but it really actually goes up to 2 to the k. And what I'm going to do is I'm actually going to call this sum s. And we're going to do something a little similar to what we did in the last problem with the triangular numbers. I'm not going to consider this sum in reverse, though. I'm going to consider this sum multiplied by the common ratio, which of course the common ratio here clearly is 2. So multiplying this sum by 2 for 2s, we get this times 2, that times 2, that times 2, that times 2, all the way up to that times 2 is just adding 1 to its power. So you'll notice that you just get like the next term in the sequence, of course. Or the next term in the sum, I guess I should say. But now we're going to subtract these two instead of adding them, because we'll notice we get this this kind of strange cancellation of inner terms. This is known as telescoping. So in fact, the term before this is indeed 2 to the k, which cancels with this when you subtract. And all the terms in between, of course, cancel out as well. Okay? So what we have left in the subtraction is just this minus the last term. S minus 2s is just negative s, actually. So we get 1 minus 2 to the k plus 1. So then dividing by negative 1, we get s is equal to 2 to the k plus 1 minus 1. Okay, and we actually saw this in a previous example. So that's great. So now we've actually shown that that's indeed true. Now what I want to do for this example, I want to do the same idea, the same process. So when you have a geometric series, or geometric sum, I should say, you can actually apply this technique. So I'm going to call this sum S. I'm going to multiply by the common ratio. First, let's find the common ratio. Now, we're actually going to be dividing by something because we're getting smaller. So here we're multiplying by 1/5. 1/5 of 40 is that. But now, how do you get to this last term? That's a little kind of weird. But as it turns out, we don't need to know how many terms there are, but it would still be nice to know what the denominator is. So maybe I can write this as 8 over 5 to the something, which makes sense because notice the next term is going to be 8 to the 5th. And in fact, maybe we can just write them out. So we get 8 over 5. I meant to say 8 fifths, sorry. Then divided by 5, we get 8 over 25. And then 8 over 125. 8 over 625. 8 over, what's that? 3125, I believe. And then finally, multiplying that by 5 gives us indeed 15625. Okay, so if you wanted to know how many terms there are, that's the first. So I'm going to start by calling this n equals, I guess we could use 0 like we used here. So it's 0, n equals 1, n equals 2, and this is all the way up to, so let's kind of count here. So we have 2, then 3, 4, 5, 6, 7, 8. So n is equal to 8 just by doing some counting there. So that's kind of nice, and we did that. Now, of course, we were able to count there. If you're not able to count, then you can at least kind of recognize the fact that this is kind of that form, like it's dividing by power of 5. You could also find the general term, which I didn't do here, but we can definitely do that as well. So for example, we know the general, since we know r is equal to 1 over 5, we know the general term for the closed form for the general term anyways, is a sub n equals, we have a0 times r to the nth. So it's a0 is 200 times 1/5 to the nth power, like that. That's a sub n. Okay, good. And if you set this equal to 8 over 15, 625, it's a little hard to solve that equation, but just divide by 200, and then I guess take log of 1/5 of both sides. That's kind of weird, but you look at powers of 1 over 5 and see where they compare. So it's still a kind of similar thing. It's not the best, kind of sloppy, but you know, you get the idea. But do we even need that is the question? Do we even need to know this is the 8th term? Well, let's see. So now that we know at least that the common ratio is 1/5, we can multiply this by 1/5. So we get 1/5 s is equal to this divided by 5, which is 40, this divided by 5, which is 8, this divided by 5, which is 8/5, and then all the way up to this divided by 5, which is 8 over, let me just write it as 5 to the, that's 5 to the 1, 5 to the 8. Let's write it as 5 to the 9th. Okay? Now subtracting, we get this minus that. If you look at the numbers in front, you have 1 minus 1/5 all times s, is how I'm going to see that. Of course, 1 minus 1/5 is 4/5, but we'll get there. And when you subtract, notice that these things kind of cancel out like this. We're subtracting. So we get cancellation of these terms. The one before this is this guy. So we get the first term minus the last term. So it's 200 minus 8 over 5 to the 9th. And then divide by this, which is 4/5. So really we get S is equal to the reciprocal of 4/5, which is 5/4, times 200 minus 8 over 5 to the 9th. So I don't know if that sounds disappointing to you. I mean, it doesn't sound super disappointing to me, but it looks a little weird still. I guess we can kind of finesse this a little more. I need more space. I'm going to erase the board and continue with this just to show how you kind of use some arithmetic to write this in a more proper fractional way. Okay, so in the last board we had this example and we got this by using that technique of multiplying S by the common ratio, which was 1 over 5, and then subtracting, we get some telescoping and we're left with these two subtracted, divided by whatever S minus its ratio is, which was 4/5 S, and then so dividing by that we get 5/4 that. Now there's actually a little mistake here, and I said this was 5 to the 8th, which is actually incorrect, because we're dividing by 5 8 times starting with 0. That's true, but if you think about it, we have 200, then 40, then 8, then 8 to the 5th, or 8 over 5, 8/5, not 8 to the 5th, sorry. Then 8 over 5 to the 2nd, and then up to this one. So this is the 8th term, but if you count 0, 1, 2, 3, 4, so this corresponds to n equals 4. So the n equals 8 term would correspond to 5 to the 6 in its denominator, because it's 2 less than the index we're at for the n equals 8th term, just by doing some counting. So in fact, I misspoke earlier when I said that this is actually 5 to the 6th. And with that being said, when you multiply by 1/5, this is actually 5 to the 7th. So my mistake there. Now we can continue this, and let's see what happens. So I'm just going to distribute, and notice that 200 divided by 4 is, I guess, 50 times 5 is 250. Okay. 5 over 4 times 8 over 5 to the 7th. You see some cross cancellation here. 4 goes into 8 twice. 5 goes into 5 to the 7th 1 time less, so 5 to the 6th times. So we end up with 2 over 5 to the 6th power. Perfect. Now we can continue this process by finding the common denominator. So I'm going to notice this is itself over 1. So what I'm going to do is I'm going to write this as a fraction over 5 to the 6th by multiplying that numerator 250 by 5 to the 6th. Now 5 to the 6th again is 15,625. So multiplying that by 250, we get 3906250. Let me see if I can write that out. 3906250. Perfect. Minus 2 all over 5 to the 6th, which again, 5 to the 6th is 15,625. Perfect. Almost there. Now, just the last thing to notice is 50 minus 2 is 48. So we get 3906248, all divided by 15625. Finally. Now, the last thing to say is what happens in general. We spoke of the general form for the partial sums for arithmetic sequences. What about that of geometric? So in general, if you have the sum from n equals 0 to k of a sub n, where a sub n is geometric, I don't think I wrote that when I wrote this out for arithmetic, but I said that the sequence we were summing over was arithmetic. So what this ends up being actually is, so let's see if we can kind of feel it out here a bit. So it's going to be the first term minus the last term. So first term, A0, minus the last term times R. Okay? All over, we're dividing by 5/4, or by 4/5 actually, which we got by doing 1 minus the ratio. So how we got 4/5 is that this is 1 minus the ratio 1/5. because you do s minus r times s, basically. So this is over 1 minus r. So that's what this looks like in closed form. Now, there's actually a little more you can do here, because remember that ak in closed form really is a0 times r to the k, then we have times another r, all over 1 minus r. We can actually pull an a0 out of this fraction. What we have left on top now is 1 minus r to the k plus 1 if you add those powers here. Known as k plus 1 for the powers r to the k plus 1. And there we go, that does it. So this is a closed form for that sum. Great, fantastic. And that's a 0 sum. Now this is nice because we don't actually need to concern ourselves with the whole mixing with starting at 0 versus starting at 1. You don't get different answers, unlike with arithmetic, we had different forms, and it was kind of weird. Okay, anyways, that concludes our discussion on arithmetic and geometric sequences and sums. Hope you all enjoyed. I hope it made a lot of sense, and I hope we're able to follow along. And I'll see you in the next video. We'll be discussing more on sequences. It's going to be a lot of fun. So again, thank you all for watching. Hope you enjoyed, and I'll see you in the next video.